We're at ETH Zurich. We're at the Hönggerberg campus. I've been here as a postdoc for 2.5 years, and very recently I became a professor. And now I have a new lab, which I got only a few weeks ago to start a new project. And right now we're in this new lab that I just got a couple of weeks ago, and you can see that it's very empty except for this one long table, which is called an optical table, where the whole experiment will be built up. So the question we explore is, how does our universe work? And in physics, we have a very successful model of the universe called the Standard Model. The problem is that even though it's very successful, and every test that we've done so far on Earth of the Standard Model has agreed with its predictions, we know that it's not complete. So there's something missing from the Standard Model, and we know this because, for example, from our astronomical observations, we know that there's more matter in the universe than what we can see or interact with or detect even. And this matter we call very mysteriously dark matter, for example. And so one of the things we know is a very big missing piece from the Standard Model is it doesn't explain or predict what this dark matter is or where it comes from. And so what we do then in fundamental physics is we try to figure out these mysteries of the universe by testing the Standard Model with ever so much more precision and pushing it really to its limits until we find where it cracks. Yeah. And you may be familiar with the experiments at CERN, where they're doing this with very large colliders. And what we can do here, it's a very different setting. There's no colliders, it's just one lab. Yeah? But what we can do here is we can measure things, aspects of the universe very, very precisely. In particular, in my lab, we measure an atom with extreme precision. And if you measure something really, really precisely, you can find tiny deviations that you couldn't see before from what the Standard Model predicts. And if you find a tiny deviation, a tiny crack, that's a door into new physics. So what do we measure in this atom so precisely to let us question the Standard Model or test the Standard Model? So when we think of an atom, we usually think of a positive nucleus and some negative electrons whizzing around, and the force between those is the electromagnetic force. And this is generally what we almost always describe an atom with. But there's also a very, very weak force there in addition to electromagnetism, called the weak force. And it's there, it's so small that compared to electromagnetism, it's about 1 trillion times tinier, okay? And the interesting thing is that if we can measure the charge of the nucleus under this force, so the nucleus has a positive charge under electromagnetism that everybody knows about, but it also has a charge under this weak force. And if we can measure that, then we can compare it against the prediction of the Standard Model and check if it matches. So where quantum physics comes in here is this idea to measure the weak charge of the nucleus has been around for a long time. Yeah. The difficulty is that when you try to measure an effect that comes from such a tiny force in the atom, you have to tell it apart from all other effects that are affecting your atom, including all of the noise that you might have around in your lab. So I came up with a technique to make this measurement that uses quantum entanglement to really isolate the part of the energy shift we're measuring that comes just from the weak force and reject every other contribution to the energy shift. And we can do this by using quantum entanglement and by selecting for a property called parity violation. That's a property only of the weak force. So the interesting thing about the era we're joining now in quantum enhanced precision measurements is that not only are we looking for answers to the biggest mysteries of the universe, we're really trying to understand fundamentally how the universe works, but also the techniques we're using come from quantum computing. Yes. So these two research areas, which seem like they have very different questions, actually work hand in hand. And a development in precision measurement with quantum techniques can be used in quantum computing and vice versa. So together these fields go, and if you do an experiment in one of them, you're actually building results and pushing forward both fields together.